Welcome to Chemistry 111. We'll continue with our math. So we last left off, we were talking about limiting reagents. What happens if we have two reactants and we have a question about how much could we possibly produce? So we have to use the limiting reagent to determine how much product could we form. We have to find out the limiting reagent and then turn grams to moles back into grams of product. Well, there's another concept we need to deal with, which is percent yield. And not all chemistry is going to be perfect. We may hope it's perfect. It works out a lot better if it's perfect, but very rarely will a reaction go 100% according to plan. In engineering, all you're trying to do is maximize efficiency. If we could burn all the energy in a car, in the fuel, cars would be going 70 to 80 miles per gallon at least. But because we lose a lot of that energy as heat, the fuel efficiency goes way down. Reactions the same way. Not all the reaction is going to go to completion. It's not all going to produce just the product we want. There could be many different reasons. Incomplete reactions. It just doesn't want to go. It just stops. The mix isn't good. We could decompose the reactant instead of have a reaction occur. Like if I heat this, it might break apart. And then we can have side reactions. We can have unintended consequences, essentially. We form something that escapes and we can't go back. So all these things will lead to one thing. The amount of product you get will be lower than what you expect you should get. And how we're going to deal with this is we're going to calculate a percent yield. So we're going to need two things, a theoretical yield and an actual yield. So the actual yield will be something you will physically measure in lab. The actual yield is something you actually got. There's no calculation involved other than you weigh it out. You maybe have to subtract out the dish it's in. But it is something we weighed out. In the magnesium oxide lab, it was the amount of magnesium oxide we got when we subtracted out the weight of the crucible. But the theoretical yield is also known as the calculated yield. It is the maximum possible yield assuming we have 100% conversion. How do we get the theoretical yield? That is the yield of product we've been calculating this last class, where we turn grams of reactant to moles of reactant to moles of product, and then moles of product back to grams of product. Those grams of product that we just calculated is the theoretical yield. It is the hypothetical yield we can get if we are fully converting from one to the other. So once we have those two numbers, all we're going to do is take actual yield divided by the theoretical yield and times by 100 to get a percent. So what will a problem like this look like? You'll be given a mass of reactant, a mass of product, and there'll be some like, what is the percent yield? So looking at that same situation that we looked at on Friday, what is the percent yield if we use 480 grams of iron oxide? I'm just going to say it's an excess of coal. We already know on Friday that the coal was excess. The iron oxide was the limiting reagent. And we said we produced 300 grams of iron. I don't know about you, I don't remember how much iron we said we were producing. So we'll go ahead and run this equation again. So we have 480 grams of iron oxide, and we produce 300 grams of iron. And the balanced chemical reaction is 2 Fe2O3, 6 carbon, let's see, 3 oxygen, goes to 4 iron, and 6 CO2. The two relevant numbers is 480 iron oxide and 300 grams iron. Those are everything we're given. Now we also need to use the molar masses. We need, what was the molar mass of iron oxide? The molar mass of iron oxide we said was about 160 grams per mole, and the molar mass of iron was about 56 grams per mole. So that's all the bits of data we need in order to answer this question. Step 1, I'm going to turn the reactant into the theoretical yield of iron. So I take 480 grams of Fe2O3, divide by my molar mass, one mole of Fe2O3. Use our balanced chemical equation to convert into moles of iron. So divide by 2 moles of Fe2O3 per 4 moles of Fe. Then I use my molar mass, 56 grams of iron per 1 mole of iron. So I've set this up, cross hatch. So grams of iron oxide, grams of iron oxide. Moles of iron oxide, moles of iron oxide. Moles of iron, moles of iron. So we're getting the calculated grams of iron. Calculated grams of iron. Doing that real quick. So, 480 divided by 160 times 4 over 2 times 56. The theoretical yield of iron is 336 grams of iron. Now, to get percent yield, we're going to take the actual divided by my theoretical times 100. Because it's grams of iron over grams of iron, the grams of iron cancel out. And so there's no grams or iron or in there. It's just a percent. Your answer is a percent. So that'd be 89.3%. 89.3. But what did I do? I turned grams to moles to moles to grams. And then I used the yield of the actual yield to calculate the percent yield. And that's what you'll do in those problems. How will we know it's a percent yield? Usually you'll say there's a percent yield problem. But another dead giveaway is usually we have the amount of reactant and the amount of product stated in the same problem. So that's two major concepts we have going on here in this chemical system. We're going to have limiting reagents and percent yields. There's one other way we're going to measure these things, and that's as concentrations. And that's because not everything is going to be set up as a solid. We've only considered the solids right now, but now we also need to consider the concentrations of a liquid mixture. Remember our solutions. Whenever you see something that says AQ, it's considered a solution, which means it's dissolved in water. When we go to have an actual reaction take place, the water is not going to be the thing that does the reacting. It will be the component that is dissolved. And so we need to consider how much of that component is actually dissolved in there. So we need to separate the solvent, which is the thing that does the dissolving, such as our water, from the solute, which is the thing that actually gets dissolved. When we look at that, we're going to have a ratio of solute to solvent, and that's going to be the concentration. It is essentially going to be a molar density. You know, density is the mass ratio of mass to volume. Well, a molar ratio would be the moles in that same volume. If we think of this as a low solute to solvent ratio, we would say a solution is dilute. There's not many atoms per solution. If it's high, we would say the ratio is concentrated. So looking here from right to left, how much red dye is in there? Not very much. So we'd say this is dilute. There's a lot of red dye on the far left. So this is a much higher concentration. It's concentrated. So based on this, you spill this on your shirt, you might be okay. You spill this on your shirt, you might as well throw that shirt away, or that's going to be your Halloween costume for the year. You look like a murder victim. So we're looking at concentration. Now, how we're going to measure that more commonly than not is molarity. There's other ways to measure this. Some of these are far more annoying. But the most common way we'll do this will be with molarity, which is literally defined as moles per liter. Moles of solute per liter of solution. Now, it's a unit to unit. So if I were to use milliliters, I would need millimoles to keep this as the same ratio. If I were to use kiloliters, and no one uses kiloliters, but if you were to use kiloliters, you would use kilomoles. So unless you're getting a smaller than a molar unit, we have to keep those in sync. But so we've seen this. When you look at a bottle of a solution that says 1 m, or 0.1 m, or 3 m, that m stands for molar. A 1 molar solution could be described as we put 1 mole of sodium chloride per a liter, but it could also be 2 moles per 2 liters, 0.5 moles for 500 milliliters. The idea is that whatever you have, this divided by this, gives you a ratio of 1. Ratio of 1. So if I calculate an easy molarity, how do we do that? So we have a molarity. What's the molarity of 3 moles of sodium hydroxide within 12 liters? If I put 3 moles of sodium hydroxide in 12 liters, the molarity would be 3 divided by 12. 3 divided by 12 is 0.25, or 1/4. So it'd be 0.25 m. What if I put 0.35 moles in 500 milliliters. Well, that'd be 0.35 divided by 0.5. Or the second one would be 0.7 m. It's 0.35 divided by 500 milliliters. You turn milliliters into liters, which is 0.5. So if you have moles and you have volume, molarity should be straightforward. But where we're going to take this is in lab, we're going to have to deal with molarities and use this to find out reaction quantities. The first thing we can do with this is dilution, and we have to understand this concept before we can move on. Concentrated solutions are easy to work with. Once diluted, they're hard to reverse. But what does dilution do? Dilution is the lowering of concentration by adding more solvent. In most situations, that's just adding more water. Oftentimes, we use a concentrated stock solution where we take a small portion out and we dilute it into a larger volume that's more useful. So if we need, we'll take a big bottle of concentrated acid, take 10 mils out, and dilute that into, say, 500 mils. And those 500 mils can run the whole class. And the 500 mils is a lot safer to deal with. But the idea here, and this is the really important part, when I take those 10 mils of acid out, that means I'm removing X amount of moles of acid. And I have X amount of moles sitting there in the beaker. When I add more solvent and dilute this to the new molarity, the amount of acid, the total amount of atoms of acid do not change. The total amount of acid atoms do not change when I add the water. The ratio of acid to water does, but the total amount of acid atoms do not change. So if when I extracted out 10 mils of acid, it has 55 atoms of acid in there, and I add water, and I add 100 mils of water. How many atoms of acid are in there? Still 55. If I drank the whole thing, I would still be getting 55 atoms of acid. The thing of it is if you try to take out smaller portions of it, you'd be getting less acid per portion because you are splitting it over a larger volume. But the amount of acid in that original 10 mils has not decreased. It has just become more spread out. If I took the students in this classroom, which is not very many, and I put it into a bigger lecture hall, I would still have the same amount of students. They would just be able to split up and move apart a little bit further apart. They'd be a little bit more dilute, but the number of students would not have physically changed. So that's what we got to keep in mind. We are not changing the amount of moles. We are only changing the ratio of moles to volume when we do a dilution. So how do we do a dilution? Starting with the center concept that the moles originally in this concentrated solution are equal to the moles diluted of this dilute solution, we can find these ratios. Remember, the one major concept is, how do we calculate molarity? Molarity is moles per volume. So if we are calculating volume, if you're calculating moles, how do you get moles by itself? You're going to cross multiply both sides by volume. Volume cancels out, and what we have is moles equals molarity times volume. That's what we're doing. Molarity times volume equals moles. So what we have right here, if we have the molarity of the concentrated solution and we have the volume of the concentrated solution, if I know how much acid was in that big bottle, and then I multiply by that 10 mils I took out, I can calculate the moles of acid I have in that 10 mil sample. Now, if I calculate what's the new volume, say that 10 mils and I took it to 500, my new volume is 500. The moles of acid has not changed, but my volume has. So my new molarity will have changed by the ratio. The volume has gone up from 10 to 50, 10 to 500. So the molarity will go down by that same ratio. So you could look at this MCVC equals MDVD, or you can simply look at it as the most common one, M1V1 equals M2V2, which says the molarity and volume of situation 1 is equal to the molarity and the volume of situation 2. So if I have 3 of these 4 values, I can find the 4th value, and that's the most common situation. I will give you a molarity and a volume, or a molarity and a volume and a molarity. But you'll have 3 out of those 4. So if I took 25 mils of a 1 molar sodium hydroxide solution and I dilute it to 100 mils, what is the new concentration? I take 1 and I times it by 0.025, and that's equal to M2 times 0.1. So what do? I need to divide both sides by 0.1 to isolate this. You divide it by 0.1 and you get the liters cancels liters, and I'm left with units of molarity. And I get the molarity has now been reduced to 0.25 from 1. So what volume would you need to dilute 50 mils of a 5 molar solution to 1 molar? So setting this up, turning 50 mils of a 5 molar into 1 molar. So say 50 mils times 5m equals 1m times volume. So I'm solving for my volume. Going to divide both sides by 1m. 1m. M and m cancel out. So you have 5 times 50 mils. 5 times 5 is 25, so 5 times 50 is 250. Because I left the milliliters as milliliters, my answer will be in milliliters. Had I turned this into liters, my answer would be in liters. But right now, since the units are the same, they cancel out. So in order to dilute 50 mils to get 1 molar solution, I would have to add another 200 to make the total 250. And so that's what I would do to dilute that down to the proper concentration. So that is some of the basic stuff we'll need to be able to do. We can further calculate the molarity from mass. And this is just combining our 2 concepts together. Instead of going grams to moles to moles to grams. We can go grams to moles to volume to molarity. So typically moles, we will not be given the moles of a solute, but we'll say the grams. Say I want to dissolve 50 grams of sodium hydroxide in water to make this solution. You need to be able to figure out what amount of sodium hydroxide we need to add. Or if I added this amount, what is the concentration? Before calculating the molarity, we must calculate the moles. So we can also use molarity and turn that back into grams easily enough. So these two practice problems. What is the molarity of a solution containing 34 grams of FeO in 1.4 liters? So I dissolved this much FeO, 1.4 liters. Let's see, 34 grams. 34 grams of FeO in 1.4 liters. 34 grams FeO. You're going to have a volume of 1.4 liters. First thing, what is the molar mass of FeO? 56 plus 16. I'm getting these from the periodic table. 56 plus 16 is 72. So what am I going to do? I'm going to take 34 grams FeO divided by 72 grams of FeO for 1 mole FeO, and then 1 mole divided by 1.4 liters. And that'll give me units of moles per liter or molarity. Moles per liter is equal to a molarity unit. So calculating that real quick. 34 divided by 72 is 0.47, then 2 repeating. Divided by 1.4. We'll just round it to 0.337. Technically, it should be 0.34. I'll leave it at 0.34 because I have 2 sig figs in there, 2 sig figs in there. I'll keep it to 2 sig figs. The second question. If I have 3.2 molar solution of hydrogen peroxide, how many grams of hydrogen peroxide would be delivered in 67 mils? So we have 3.2 m H2O2. We have a volume of 67 mils. And we want to go grams. So step 1 would be M times V gives you moles. And then we're going to go to grams. So 3.2 moles per liter times, what's our volume in liters? 0.067 liters. Cancels out and gives us moles. And then the molar mass, I forgot to do this. 16 times 2 is 32, plus 1 times 2 is 2, so 34. The molar mass is 34 grams per 1 mole. Mole. What do we have left? Grams. So in this case, I have 3.2 times 0.067 times 34. Doing that delivers 7.3 3 grams of hydrogen peroxide. 7.3 grams of hydrogen peroxide. Apparently my math is a little off somewhere. I rounded between this step and that step. Yeah, that's fine. But I don't know how many more slides we got left. So where we're going to go with this, the final application will be what we're doing in the lab, which is a titration. A titration is using the M1V1 equals M2V2 equation to find an unknown concentration of a known compound. So we're going to take our known solution, which will be our standard, our titrant, and we're going to slowly add, which is we're going to titrate this into a solution of unknown concentration. And the idea here, when equal, which is our stoichiometric amounts, when equally molar amounts of a solution are added, we reach what's called the equivalence point. When the moles of A equal the moles of B, when they completely neutralize each other, when the reaction is fully done, we have reached the equivalence point. This is commonly done with acids and bases. When you reach the equivalence point, you have neutralized all the acid has neutralized all the base has neutralized all the acid. We will often use a colorimetric indicator, but sometimes we'll use a pH meter. We'll try to find this equivalence point. The colorimetric indicator will be one color under acidic conditions and another color under basic conditions. When we have just acid in there, it'll look one way, and just base, it'll look another way. And we're going to be measuring the point where it changes colors permanently. It goes from acidic conditions to basic conditions, and we're going to use that to figure out at what point were the moles of acid and the moles of base equal. And we will use that with the M1V1 equals M2V2, but we're going to change it, the descriptors, just to make it a little bit simpler. We're going to say MAVA equals MBVB, but it is the same equation. It is the same equation. It's going to be looking at the moles of A is equal to the moles of B. The moles of acid is equal to the moles of base. This will work with most simple monoprotic acids and monohydroxyl bases, such as sodium hydroxide, HCl. But it's not going to work so nicely with H2SO4 that has 2 protons, or MgOH2, which has 2 hydroxys. So, but we will be doing that, and I'm going to actually, yeah. We will leave this example till Wednesday. We'll leave that example to Wednesday. So we'll finish off this chapter Wednesday with this example. Be perfectly ready to go into lab, because I think this lab is a titration lab, if I'm not mistaken, and we're going to be titrating acid with base and seeing it change pretty colors. It will be an easy lab, especially if you understand the M1V1 equals M2V2 equation. That's where we're going to go. Thank you for your time.